yeah, thank you for inviting me to talk. So what I want to talk about today is gaps between primes, and particularly small gaps between primes. So the basic question you're all familiar with, we think about the number p and the primes p and the gaps of the length h, and we're asking, does it happen infinitely often that there is a prime p so that p plus h is also prime? And of course, for odd numbers h, this is impossible. And for even numbers, we think that it always happens, but we are impossibly far from proving anything like that. So we think about an easier question, so to say. And an easier question is, if I give you a few different prime gaps, can we at least show that one of them appears infinitely often? And one specific case of that is thinking about what's the smallest number for which we can show that below that there's a gap that appears infinitely often. And in that direction, Goldstein-Vincent-Yildirim had a very nice first result, which was that on the one hand, the smallest gap between primes up to x doesn't grow too fast. And on the other hand, if we have an improvement on the Bombieri-Vinograd theorem, which talks about the error terms for primes in arithmetic progressions, then we can show that there's a gap between primes that appears infinitely often. And the issue with this was a very nice result, but the issue with it was that this improvement on the Bombieri-Vinograd theorem, which is from 1965, we still today don't have an improvement of the type that would have given us boundary gaps between primes with the approach that Goldstein-Vincent-Yildirim took. And so Zhang made his big breakthrough in 2013, where he showed that there's a prime gap below 70 million that appears infinitely often. And lots of people worked on improving that, and today the smallest number for which we know that there's a gap that appears infinitely often is 246, which is still quite a bit away from 2, but it's certainly much smaller than 70 million. And of course, we can also think about gaps between 3 and more primes, and for that there's also various results. And the expectation is that if we look at gaps between m plus 1 primes, then there will be then if we look at the length of about size m times log m, there will be a number below that that appears infinitely often. And as you can see, e to the something times m is much larger than m times log m. So the node results, they're much worse than what we think to be true. But this is the best we got. And so what I want to talk about today is mainly the GPY method of Goldstein-Vincent-Yildirim, which is used to prove all the results on the previous slides, and particularly how primes in arithmetic progressions feed into that method. So what's the connection between short gaps between primes and primes in arithmetic progressions? So this is the main topic of this talk. And before I start talking about the GPY method, maybe I should say a little bit more about equidistribution estimates for primes in arithmetic progressions. And the basic question is, I have a sequence A plus Q, A plus 2Q, and so on. And I ask, are there infinitely many primes in that progression? And if A and Q are not co-prime, then trivially they cannot be more than 1. But if they are co-prime, and then what we know from the Siegel-Waldfels theorem is that the number of primes up to x in an arithmetic progression, if we make the x large enough, then about 1 over phi q are in any particular progression. So basically, there's phi of q, so Gaussian function of q, different arithmetic progressions for a given gap size q, and we are equally likely to be in any of those. So that's why we say the primes are equidistributed. But this is just an asymptotic, so it's not very practical to work with that in Ceph methods and so on. So we need to know more about the error terms. And for that famous result is the Bombieri-Vinograd theorem, which says that if I look at the difference between the number of primes in this arithmetic progression and the expected number of primes in the arithmetic progression, so this is the error terms, and I take the maximum over all the different residue classes, and I think about all the different prime gaps up to a little bit less than x to 1/2, then we know that this is bounded by x over log x to the a. And because we are thinking about approximately x to 1/2 different things, that means that at least on average, the error term is no bigger than x to 1/2. And this is the size of the error term that's predicted by the generalized Riemann hypothesis. So while we don't know that the generalized Riemann hypothesis is true, we know at least that what's predicted by it is true on average. And we also think that we can actually get much smaller error terms on average, so x to the epsilon for any small epsilon. And this is exactly the improvement of Bombieri-Vinogradov that I mentioned earlier. So Goldstein, Binz, and Yildirim, they could have gotten boundary gaps between primes if we could have gone a little bit beyond 1/2. So if we could get an average error term smaller than x over 1/2 minus epsilon, that would have been good enough. But unfortunately, even today, we don't have such an improvement. So if we want to think about all the different modulo Q, then for the average, we cannot get anything better than x to 1/2 than some power of log. And so we need to think about making an improvement in a different way. So this is kind of the most restrictive condition. We are thinking about all the different moduli. And to make an improvement, a good thing to do is to not think about all different moduli, but to think about ones that have a nice factorization. So on the one hand, one could make an improvement by dropping the condition that this upper bound should not depend on the chosen residue class A, so not taking a maximum, but fixing the residue class, and letting the upper bounds depend on the chosen residue class. And there's several nice results in this direction, for example, by Maynard, Pascal, and Lichtman, who are in the audience here. But this is not a good thing to do for the GPY method. So there we don't want the upper bound to depend on the residue class. And so instead, we just drop the condition that we are taking a maximum, but we are still thinking about upper bounds not dependent on the residue class, but we're making the restriction that our moduli now, Q now have lots and lots of small prime factors. Because if we have lots and lots of small prime factors, that means we have lots of flexible factorizations, and that's good if we want to work with things like exponential sums. And so if we think about only considering moduli Q, which are product of small primes, and say, let's say all the prime factors are less than delta, and then we can go beyond 1/2. So there's several relationships. So the Polymath project, for example, got that we can work with 600 omega. So omega is how far we go beyond 1/2 over 7 plus 180 delta over 7, but delta is the size of the prime factors. And we got an improvement to 80 omega plus 80 delta over 3 less than 1. And if we take the delta to be very, very tiny, that means that we can go up to x to 0.525 instead of x to 0.5, which is in the Bombieri-Vinogradov theorem. So basically, on the one end, we have the Bombieri-Vinogradov theorem, which works for all the different moduli, but can't go beyond 1/2. And on the other hand, on the very restricted sides, so when we are very restrictive with the moduli that we consider, with having lots and lots of small prime factors, we can go up to x to 0.525, and then we can do various things in between. So if we don't want all the prime factors to be tiny, have a few larger ones and so on, then we need to stop somewhere between 0.5 and 0.525. So there's various equidistribution estimates in between, and all of those feed in some useful way into the GPY method for proving boundary gaps between primes. And so this works as follows. The question is, we want to show that there's a prime gap that some prime gap that appears infinitely often, and so we think about a tuple h1 up to hk, and we ask, is it the case infinitely often that if I shift this tuple by n, that there's at least m plus 1 prime factors? Because if this is true, so if m plus 1 entries of this tuple are prime, then we know that there is m plus 1 primes that are no more than hk minus h1 apart, and that gives us an upper bound on small prime gaps. And the Hardy-Littlewood conjecture says if we take any tuple, so one restriction is we can't have a prime where all the h1 up to hk covers all the residue classes modulo that prime. Because, for example, if we think about 2 for 6, then if we shift this, there's always something that's divisible by 3. So that's bad. But if we avoid this case, so if we say that h1 up to hk doesn't cover all the residue classes for any prime, then the Hardy-Littlewood conjecture says that we will get infinitely many tuples where all the entries are prime. And the Hartley Littlewood conjecture is unfortunately open for any choice of k greater equal 2, so that's not very helpful. But we can think about the weaker statement of not all the entries being prime, but just some of them being prime. And the longer the tuple is, the easier this is to prove. So basically, the question is, how small can we take k and still prove that there's infinitely n many choices of n where some of the entries of this shifted tuple are prime. And the way the GPY method approaches this is we're thinking about a weighted sum. So on the one hand, we are summing over the entries of the tuple, and we're asking how many of those are prime. And then we're subtracting m and multiplying this by a weight function. And if it is the case that this quantity is bigger than 0, well, because the weight function was chosen to be non-negative, that tells us that one of those differences of the number of primes in the entry and m must have been greater than 0, and that means that there have been m plus 1 primes in our tuple. So all we need to show, in quotation marks, is that there is some suitable weight function nu, so that this quantity here is greater than 0. So this is the basic setup of the GPY method. And now the big question is, how can we choose the weight function nu in order to make this quantity greater than 0? So the idea, the nice idea is that if it's bigger than 0, then we have proven that there's m plus 1 prime entries. But this is all good in theory, but if we can't find a suitable weight function nu, then that doesn't really help. And if we look at this quantity, well, on the one hand, we are subtracting m times the sum of the nu. So we are summing up nu over this whole interval. And then on the other hand, we are summing it weighted by prime indicator functions. And so that means that the thing we want to make big and positive is weighted by prime indicator functions, whereas the thing we are subtracting is just the whole sum. And that means we are in trouble if the nu is large. A lot of the times we're getting a 0 for the prime indicator functions. And so the idea is we want the weight function to be only large if n plus hi is prime for some n, but this is too tricky. So actually, the idea is to pick a weight function which is large when n plus hi is prime or a product of just a few primes. So this can be done with sieves. And the sieve weights that Goldstone, Binz, and Yildirim chose, they were a bit too weak to give a result with just a Bon-Biara-Vinogradov theorem. But currently, the best known weights are the Maynard-Tarr sieve weights. And for those, they look as follows. So we are picking a smoothed out indicator function for the primes and products of few primes. And we are applying this to each of the n plus hi to make sure that the function is not too large if there's no primes or products of few primes. And then we are squaring it to make the weight function positive. And this is a very flexible construction because for each of the indicator functions that we have, they're constructed using some choice of function f, and this choice of f is very flexible, and the coefficients c, j are also very flexible. And so that means we are not just constructing one choice of weight functions, but lots of different ones. And then we can pick out the one which gives us a nice large result. So basically, we started off with this quantity, weight function times indicator functions minus m, which we want to make larger than 0. And with the Maynard-Tarr sieve weights, we want to show that this is bigger than 0. But the problem is, well, we have written down a weight function, but we still don't know what n is. So we need to somehow compute asymptotics for this expression n. And the way this is done is we need to figure out what the sum of the nu n weighted by the prime indicator functions is. And to do so, we just plug in the expression. And plugging in, we get some copies of the functions lambda, which are sums over the divisors of n. And then just rearranging, we end up with a sum over divisors d. And pulling them outside, it's just a sum over d. And then on the inside, we have all functions f, which were used to construct indicator functions. And on the very inside, we have the prime indicator function, where we just made a change of variables from n plus hi node to m. And so we see that if we just plug in the Maynard-Tarr sieve weights, suddenly here at the very end, we get a count for primes in arithmetic progressions. So this is where the primes in arithmetic progressions appear. So suddenly we have primes in arithmetic progressions, and they are the key to computing at asymptotic for this quantity n in the GPY method. But summing over primes in arithmetic progressions is hard, and so we want to replace this by something nicer, and this is where equidistribution estimates come into play. So instead of having the sum of primes in arithmetic progressions there, we want to just replace it by the expected number of primes in arithmetic progressions, which, glossing over various issues with common prime factors and so on, is just x times the dosage function applied to our factors di times log x. And this is all nice and good, provided that the error terms are not too large. So this is why we need equidistribution estimates, because we make this replacement, and we don't want to have that the error terms outweigh now the asymptotic for the main term. And we have a suitable asymptotic provided we have an equidistribution estimate. And so we are summing over all the error terms. And the error terms are only relevant if the factors di actually contribute to our big expression. And here we look and we see we have log x di is being entered in the functions f that we use to construct the indicator function. And so the log x di only contribute if they're actually the support of f. So when you construct the Maynard-Tower sieve weights, you need to make sure that their support corresponds to a known equidistribution estimate for primes in arithmetic progression. So the connection is, so if I quickly summarize, our goal was to give an upper bound on small prime gaps. And for that purpose, if we rearrange n, we need to show that the sum of the Maynard-Tower sieve weights weighted by prime indicator function over the Maynard-Tower sieve weights is bigger than m. And so we need to choose functions nu that make this left-hand side big. And so we want to optimize the choice of functions f and coefficients tj in the sieve weights. And for this optimization problem, we are only allowed to use functions fji, for which the supports correspond to something like the Bombiaro-Vinograda theorem or some equidistribution estimate for smooth moduly or something like that. So this is the connection. And if we make it a little bit more precise, then optimizing over lots of different functions fji is not really practical, but luckily by integration and linear combinations and so on, they can be translated to a single function f. And so basically, from making this quantity bigger than m, the optimization problem becomes making an integral of a function f bigger than m. So we have an integral and the function f, which is squared at the bottom, and at the top we are integrating first and then squaring. But basically, now we have a very concrete optimization problem to solve. It's still a very difficult optimization problem, but it's a concrete problem. And we need to optimize our functions f, which correspond to good equidistribution estimates for primes in arithmetic progressions. And here, the condition was that the log x di were the support of the individual sum functions fji. And now that we have combined into a big function f, we just need the corresponding tuples of log x d1 up to log x dk to be in the support. And so now we can write down how this is connected to the Bombiaro-Vinograda theorem and such. So for example, what we could say is that we're making the support of our function so that it's a simplex. So the sum of the t1 up to dk is bounded by 1/4, because then the sum of the log x di is bounded by 1/4, and because we have two copies of them, their product is bounded by x to 1/2, and that would correspond to the Bombiaro-Vinograda theorem. Or we could do something with smooth moduly, where we say, okay, each of the ti's is smaller than delta, because then the log x di's are smaller than delta, and then each of the factors di is less than x to the delta, and then we could think about equidistribution estimates for smooth moduly. Or we could go anywhere in between those two cases. So thinking about the ti's being restricted to specific intervals, which correspond to nice factorizations, which correspond to good equidistribution estimates. So in the Bombiaro-Vinograda theorem, we can go only up to 1/4. And if we have better equidistribution estimates, we may go beyond the 1/4, but then we have the issue that some of the factors di are restricted to certain intervals, and so we are gaining some area, but we are losing some other area. So for a concrete example, let's look at what happens for large M. So if we're thinking about situations where we're thinking about gaps with many, many, many primes, then we're thinking about having lots and lots of tuples of a very long length k, and that means that individually, if we have the sum being less than 1 over 4 plus a little bit, then each of the individual variables is not very large, and so this restriction of making them less than some delta is not a big problem, and so we are getting a lower bound for our optimization problem of 1 over 4 plus omega times log k, where the omega is how far beyond the 1/2 we are allowed to go for the equidistribution estimates. And then this is bigger than m, which is what we need for the GPY method, provided we have e to the m over 1 over 4 plus omega for the length of our admissible tuple. So here we see where the e to the m comes from, and which is much, much larger than what we expect for the true bound to be. And so the short length of the shortest admissible k tuple is bounded by k log k, and so putting this together, we get a nice upper bound of e to the 3.8075 m. Now, if we think about gaps between, let's say, 3 primes, then it becomes a bit more tricky, this relationship between how big do we allow our support to be, so how far do we go beyond 1/4, and how small do the individual variables need to be to use equidistribution estimates for smooth modeling, because now we don't have, the tuple is not that long anymore, and so we might lose something in terms of area if we make the delta too small. And this problem becomes especially significant if we think about gaps between just 2 primes. So thinking about gaps between 2 primes, the Polymath project doesn't use equidistribution estimates for smooth model, but just the Bombier-Vinograd theorem. And I want to highlight a little bit the issues here that are with going beyond the Bombier-Vinograd theorem and using newer equidistribution estimates. So in the Bombier-Vinograd theorem, we have a certain region that we are optimizing over. And the idea is if we are optimizing our bigger region, then we have more functions to think about, and so we should get a better result. But in terms of practical considerations, we can't optimize over all the different functions f there are. We need to make some restrictions so that we can solve our optimization problem. And so one idea that Polymath used is to think about certain symmetric polynomials and go just up to a certain degree, because afterwards it just becomes too much for a computer to handle in a finite amount of time. So this is, and let's say we're thinking about, so in the Polymath project, they thought about symmetric polynomials going up to degree 23, I think. But here I just did a quick comparison, and so I'm choosing a smaller degree so that we can look at some nice numbers. So for the Polymath project, they got out that if we choose a support, a simplex of size going up to 1 over 4, which meant that we can use the Bombier-Vinograd theorem, then going up to degree 23 for our symmetric polynomials, we would be just above 1. And if we go down to just thinking about symmetric polynomials of degree 7, then we get something that's a little bit smaller, so 0.9697. Okay, now instead of wanting to use the Bombier-Vinograd theorem, let's say we want to use equidistribution estimates for smooth modeling. Well, then we have to think about, on the one hand, how small do we want our prime factors to be? So that's the choice of delta. And then for that, we can go a bit beyond the 1/2 in the Bombier-Vinograd theorem. And so this omega is how far we can go beyond. And if we, for example, choose the delta to be 0.02, and we have 50 variables, then the 50 variables are an average of size 0.005. So we have a region where the individual variables are going up sizes up to 4 times the average size, which means we don't lose much in terms of area. And if we go a little bit beyond, we see that actually the area of the region for the smooth model is a little bit bigger than the area that Polymath optimized over. And yet we get a much, much worse result. So we are optimizing over a bigger area, but we get a worse result. Why is that? Well, the issue is that the areas, they're not like a strict subset of each other. So the area we gained is actually not contributing as much as the area we lost. So there's not just considerations of how big of an area are we optimizing over, but actually is the area that we're optimizing over a good input for this optimization problem? Does it contribute a lot? And if you're thinking about the symmetric polynomials, here a lot of the contribution came from the areas we lost, and we didn't gain so much from the areas we added. So that's a bit unfortunate. And you can also think about combining those areas, but then you're not really using equidistribution estimates for smooth model anymore. You're already thinking about, okay, I have one large prime factor and several small prime factors, and that way, and such equidistribution estimates are also available. It just takes more work to use them. So then we gain even more area, and still we don't get much of an improvement. So I guess what I want to finish this with is by saying, unfortunately, the big obstacles for gaps between two primes and using newer equidistribution estimates is that you have to think a lot about the areas they correspond to. So the areas that we add with this new equidistribution estimates and the way we combine them with the older ones, are they actually useful for the polynomials that we are optimizing over? And so it's unfortunately not a simpler case of just throwing the smooth model and Bombieri with the Grade theorem together to get a nice result. One has to do a lot more work if one wants to have any hope of getting an improvement there. And I think I'm almost out of time, so I'm going to finish there.